Hello everyone, myself Dr. Golam Sarkar, Assistant Professor in the Department of Applied Science, Golden Institute of Technology. In today's lecture video, I will discuss about briefly on the topic Introduction to Differential Equation. So first of all, we should learn what is differential equations, what does it signify, what are the application of differential equation. We will answer all these questions in this lecture video. Okay, so first we'll come to what is differential equation. Okay, so an equation involving derivatives of one or more dependent variables with respect to one or more independent variables is called a differential equation. For example, as you can see, I have taken 5 examples of several kind of differential equations. Okay, now comes to the first equation. Here dx dt equals to ax, where a is a constant and x is the dependent variable and t is the independent variable. Similarly, for the second equation, here y is the dependent variable, t is the independent variable. For this equation, theta is the dependent variable, t is the independent variable. For all these three equations, dependent variables are what? X, y, and theta, and independent variable is t only. Okay. Now, in this equation, these two equation, u is dependent and x comma t is the independent. Right? Now, to talk about them, we shall classify differential equation by type, order, and linearity. First, we come to type. Differential equation can be classified into two types. One is ordinary differential equation and the one is partial differential equation. What is ordinary differential equation? A differential equation involving ordinary derivatives of one or more dependent variables with respect to a single independent variable. That is important. With respect to a single independent variable is called ordinary differential equation. For example, 1, 2, 3 equation number. As you can see, in these three equations, these are the examples of ordinary differential equation where the independent variable is the t only. Okay. So if in a differential equation there is only a single independent variables, that time we'll say that equation is an ordinary differential equation. Right? Now, partial differential equation. A differential equation involving partial derivatives of one or more dependent variables with respect to more than one independent variables is called partial differential equation. That meaning is in the partial differential equation, there must be more than one independent variables. For example, equation number 4 and 5. As you can see here, u is the only single dependent variable, but x comma t are the two independent variables for these two partial differential equations. Okay, so these two are the example of partial differential equation where we have more than one independent variables. That's a they are x and t. Okay, now is it possible to get more than one dependent variables in a differential equation, whether it is a ordinary differential equation or partial differential equation? Yes, it is possible. If I take these two examples of a system of first order differential equation, that is dx dt equals to, suppose say 2x plus 5y and dy dt equals to suppose 3y plus 2y. See, this is a system of equation, and this is clearly an ordinary differential equation because there is only one independent variable. But you see, in this equation we have two dependent variables x and y. Okay, so it is possible to get more than one dependent variables in a differential equation, right? Another example, if I take for PD, where we have more than one dependent variable, that is, if I take this equation, del u del x plus del v del y equals to 0. You see, we have more than one independent variables and partial derivative terms are there. Okay, so clearly this is a partial differential equation, but you have more than one dependent variables u and v in this differential equation. So it is possible to get more than one dependent variables in the ordinary differential equation as well as in the partial differential equation. Okay. Now, what does ordinary differential equation signify? Right. So, to understand this, we'll take a simple example. Suppose if I take few points and connect all these points. Take this point. P1 is suppose say 0 to P2 is 1 3, P3 is 2 4, P4 is 3 5, and so on. Now P1 is 0 to, that is, suppose say this is my x axis, this is my y axis. Okay, so P1 here, take another point, P2 here, take another point, P3 here, this is my P4, and so on. Now, if someone trace all these points, what you will get? You will get a straight line, this, and if I extend this line, you will get this. Now, you see, instead of telling all these points P1, P2, P3, P4, we can represent all these points through a straight line. Y equals to x plus 2. Okay, so all this point passes through this straight line, y equals to x plus 2. Right? If you substitute x equals to 0, you will get 2, y value 2. If you substitute x equals to 1, y equals to 3. For x equals to 2, you will get y equals to 4, and so on. So, this point represents nothing but a straight line which is defined by y equals to x plus 2. So, same concept we can extend for a solution of a differential equation. Right? Now, we'll take an example of a circle of radius a. Now, if I take a equals to 1, you will get a circle of radius 1 this. If I take a equals to 2, you will get this circle. If I take a equals to 3, you will get this circle, and so on. Now, this family of circles, x square plus y square to a square for various values of a, gives you what? Gives you nothing but if I differentiate this expression with respect to x, what you will get? 2x plus 2y dy by dx equals to 0, or dy by dx equals to minus x by y, right? This, that represents what? That the slope of the family of circles, this, is nothing but minus x by y, or the solution of the differential equation dy dx equals to this is nothing but the family of circles this. Okay. Now we'll take another example. If I take Suppose say y equals to x square plus c. It is a parabola, right? Now for different value of c, you will get different parabola, family of parabolas. For c equals to 0, take another value of c, you will get this. For another value of c, you will get this. If we take c negative value, you will get this. Okay. So all these family of parabolas, the slope of this parabolas is nothing but 2x at any point x comma y, or in other words, that the solution of the differential equation is nothing but the family of the parabola, which is represented by y equals to x square plus c. So if I summarize these two examples, what we get? That the solution of a differential equation gives you a family of curves. Okay. Now comes to order and degree of a differential equation. The order of a differential equation is the order of the highest order derivative involved in the equation. So if in a differential equation there are some highest order term, okay, so that will be the order of the differential equation. We'll come to it through several examples. Next one is degree. The degree of a differential equation is the power of the highest order derivative involved in the equation after the equation has been expressed in a form of free radicals and fractions as far as the derivatives are concerned. What is the meaning of this? Now, if you take the simple definition of the degree of a polynomial, what you will get? Suppose f of x is a polynomial of degree n, then we can express this polynomial in the form of a naught x to the power n plus a1 x to the power n minus 1 plus a2 x to the power n minus 2 plus dot plus a n minus 1 x plus a n, where a not equals to 0. Then the degree of the polynomial is what? N, right? The same concept we can extend for the degree of a differential equation, right? Here, each power n minus 1, n minus 2, and so on must be a whole number. That is, this power uh, is either 0 or a positive integer, right? Now, we take these examples. For this first one example, you see the differential equation in the form of del 3y del x cube minus 15x del y del x equals to this. So the highest order derivative term is what? This term, and it has only power 1. So order is 3, degree is 1. Similarly, here the highest order derivative term is here d2x dt square. Here also another term. But you see that one term has the power 2. So the degree is 2 and order is 2. In this example, you see for this differential equation, the highest derivative term is this and it has power only 1. So degree is 2. Sorry, degree is 1 and order is 2. But for the last example, you see dx dt plus sine of dx dt equals to 0. For this differential equation, order is clearly 1 because the higher derivative term is this dx dt. But we cannot define the degree. Why? If you see in the definition of degree of a polynomial, we have finite terms. But you know that sine x is an infinite series. X minus x cubed by factorial 3 plus x to the power 5 by factorial 5 minus this and so on. Right? So we cannot get a finite power of this derivative term. So we cannot define the degree of the differential equation. So For this differential equation, degree is undefined. Okay. So when we define the degree, we only look for the derivative term of the dependent variable, right? Uh, Take this example. If I take d2y dx square plus x y square equals to 0. You see there is only one derivative term this, and this is the only highest derivative term. So order is what? 2. Degree is 1 for this differential equation. But if I take this d2y dx square whole to the power 1 by 4 equals to dy by dx, this equation. Now you see the highest derivative term is this d2y dx2. So clearly order is 2, but it has power in the in which form? Rational form. Okay. So to define the degree of the differential equation, we have to make it, or we have to make the derivative terms rational free. Okay. So to make the differential equation, to make the derivative term rational free, what do we get? We can express this equation in this form of d2y dx square equals to dy dx equal to the power 4. Okay. So the order is 2 and degree will be 1 here because the highest derivative term has the power 1. Okay. Now, if I take another example, suppose say take this dy dx equals to y to the power 1 third. So tell me what is the order and degree of the differential equation? You see the highest derivative term is what? 1. So order will be 1 and it has the power 1. So degree will be 1. Right? So when we concern about the degree of a differential equation, we only look for the power of the each derivative terms. If the each derivative terms have power in the form of whole number, then we can define that the highest derivative term is the power of the highest derivative term is nothing but the degree of the differential equation. Okay, since here the dependent variable y has the power in the rational form, we are not concerned about it. We only concerned about on the derivative terms. If the each derivative term is fractional free, power as fractional free, then we can define the degree of that differential equation. Okay. Now comes to next definition. What is linear differential equation? A linear ordinary differential equation of order n in the dependent variable y and the independent variable x is an equation that is in or can be expressed in the form of this form. Any linear ordinary differential equation of order n can be expressed in the form of this, where a naught, a1, a n minus 1, and a n are the coefficient of x. Okay, or this expression can be written in the form of L of y equals to this. What is L here? L equals to a naught dn dx to the power n plus a1 dn minus 1 dx to the power n minus 1 and so on. Okay, so if you substitute L of y, you will get this expression. Okay, and this L is called the linear operator. Okay, now if you observe this equation, you will see that the dependent variable y and its various derivative occur to the first degree only. You see, each derivative term has power 1. Okay. Next one is that no product of the dependent variable y and its derivatives are present. Can you see any product of the dependent variable and its derivative term in this expression? No, you cannot see. And that no transcendental functions of y or its derivative occur. That means there should not be any sine, cos, tan, log, exponent function of the dependent variable y or its derivative. If it appears in a differential equation, that time we'll say that the differential equation is not linear, that is non-linear. Okay, so example of linear differential equation is what? This, you see, each derivative term has power 1 and there is no product of the dependent variable and its derivative. Okay, so this is an example of linear differential ordinary differential equation. For this example also, each derivative term have power 1 but no product of the dependent variable y and its derivative. So this is an example of linear differential equation. Okay, what is nonlinear? A nonlinear ordinary differential equation is an ordinary differential equation that is not linear. For example, if you see this example, you see the derivative term dy dx has power 1, but you see this is in the form of the product of the dependent variable y and its derivative. Okay, so you see in the linear differential equation no product of the dependent variable y or its derivative present. If it presents, then the differential equation is not linear, that is non-linear. Okay, similarly you see the dependent variable y is in the function of sine. Okay, so if you see some function, trigonometric function or exponential function or logarithm function of the dependent variable and its derivative in a differential equation, then that differential equation is nonlinear, right? Similarly, here the dependent variable y has power 2. Okay, so it has not power in a linear form. Okay, so this is also another example of nonlinear differential equation. We'll take few examples more to give you a clear idea about the linear and nonlinear differential equation. If I take this equation dy dx plus e to the power y equals to 0, you see the differential equation has a term which has the exponential power of the dependent variable. So this is a nonlinear differential equation. But if I take this equation dy dx plus e to the power x equals to 0, then this equation is linear. So what is the difference between these two equations? That can, or in other words, can you express this differential equation in the standard definition? That is this, in this form. You see, you cannot write this differential equation dy dx plus e to the power y equals to 0 in this form, standard form of the linear ordinary differential equation. If you can express this equation in this form, then we can say that this is a linear differential equation. So clearly we cannot express this equation in this form. So it is a nonlinear equation, nonlinear differential equation. But if I take this example dy dx plus e to the power x equals to 0, you see I can express this equation in this form, right? Where e to the power x will be what? E to the power x will be this function b of x. Okay, so this is a linear differential equation. Okay, take another example. If I take this d2y dx square plus y dy dx equals to 0. Again, you see I cannot express this equation in the standard form, this form, because you see the coefficient of this first order derivative dy dx as the dependent variable, or this term in the form of product of the dependent variable y and its derivative. So if in a differential equation the dependent variable and its derivative are in the product form, so that type of equation is called non-linear. Non-linear. Okay. Another example, if I take this equation d2y dx squared plus x to the power 4 y equals to 0. Now you see, I can express this equation in this standard form. So clearly, this is a linear differential equation. So if I summarize that if in a differential equation, the dependent variable and its product, the dependent variable and its derivative are not in the form of product, or there are no sine, cos, logarithm, or exponential function of a dependent variable. Okay, so that type of equation can be expressed in the form of this, and we will say that that type of equation is nothing but a linear ordinary differential equation. Okay, now what are the application of this differential equation? There are a lot of applications of differential equations in physics, mathematical biology. Every engineering branch has a lot of applications. I have taken 3 4 examples here. First one is Newton's law of cooling. You see the expression is in the form of differential equation. Okay. Another one is growth and decay rate, that can be also expressed in the form of differential equation. Spring mass system. You see, this is a second order differential equation. RLC circuit. This is also a second order differential equation. So it has lot of applications in every engineering branch. So we stop here. If you like this video, I will continue this lecture series on the differential equation. Thank you all.